we all ready? Great. Hello, everybody. Welcome and thank you so much for coming. We are Group 2 for the University of Florida's Aerospace Design 2 class this semester, and this is our final presentation. So a quick kind of overview of what we're discussing today. We're starting with introductions, both to our group and the project itself. Then we are moving into the design process that's separated into component design and then the analysis that we did. After that, we have our iterative fabrication and test process, and we're going to end with some conclusions that we've gotten. So a quick view of our group. We are all seniors in aerospace engineering this semester. We're either graduating in the spring or the fall. And like I said, all of us are aerospace engineering majors, and some of us have the dual degree with mechanical engineering as well.
Okay, so the primary objective of this project was to design, build, and test a radio-controlled airplane, an RC aircraft. We had some requirements that we needed to meet. We needed to be able to have the plane take off under its own power. There could be no assistance from the group. We couldn't push it or throw it. It needed to fly around a track, which you can see on the slide. It had to go around 3 times. This was later reduced to just a single lap for ease of flight. And it also had to be able to safely land without acquiring any major damage. We also had some constraints on the flight and the aircraft itself. The maximum time for the flight was 5 minutes. And also we had maximum dimensions for the aircraft in any direction at 8 feet. That included wingspan or nose to tail. And we also had a maximum weight of 55 pounds, but that ended up being a very large constraint, and we didn't meet it at all, or we didn't reach that high at all.
So for the initial design process, we took all of these project requirements into account in order to come up with some rough estimations for critical aircraft parameters. So some of the estimations were, you can see here in the table on the right. The main thing we focused on was the weight initially. And how we approximated that in the beginning was we took the volume of the fuselage, the wing, and the tail as a series of rectangles, which we added together and multiplied by the density of PLA, which we then took that weight and added it to some rough calculations for the weight of the motor and the avionics equipment to get that figure you see on the right. Similarly, we did the wing loading based on that weight and the area of the wing. And we optimized it to fall within a range that would optimize stall speed and the maneuverability of the aircraft. And then finally, we picked the lift and drag ratio to be about 20. And that was based on estimations we'd seen online from similar sized aircraft. And then we used that to derive the power to weight ratio for our plane in particular.
So our Reynolds number was calculated to be 125,000. We did this using the average speed required for takeoff, which was 27 miles per hour. This Reynolds number falls within the range of turbulent flow. So we needed to pick an airfoil shape that would ensure stability. We compared the NACA 2412 to the 4412. Both are common airfoils, which is why we picked these. The 2412 is better suited for lower speed applications, which is perfect for an RC aircraft that is moving at slow speeds. And it also has a lower drag coefficient. The coefficient of pitch versus angle of attack graph on the right, you can see that in that graph that the 2412 is less destabilizing than the 4412 because it's less negative. So this is why we ultimately chose the NACA 2412 as our wing airfoil. We then calculated the distance for takeoff using kinematics. We found this to be 35 feet. This was well within the constraints of the runway, so we did not have to worry about that.
So for our wing geometry, we first estimated the wingspan at 48 inches by looking at similar RC aircraft online. But after running XFLR5 analysis, we determined that we needed to increase the wingspan to 63 inches. And in this analysis, we found we needed an instant angle of 5 degrees for takeoff. We had a root chord of 9 inches and then a taper of 0.5, which would get us a tip chord of 4.5 inches. And with that, that got us a sweep angle of 14.5 degrees. And we found that for general aviation aircraft, a sweep angle of 10 to 20 degrees is pretty good. We chose to put the wing high on the fuselage in order to increase the lateral static stability. And in doing so, that meant we didn't have to add dihedral, because dihedral also increases lateral static stability. And without dihedral or twist, we were able to make manufacturing easier. And to reduce drag, we added sharp wing tips. Next slide, please. For the control surfaces, we opted for the ailerons only to do ailerons and no flaps, as flaps are really good for only takeoff and landing and lower speed flight. And then they would add an extra servo, which would complicate the manufacturing process, and we were already at max amount of servos we could use. We found in a journal article to use, or the aileron should be about 20% of the wing. And then we found in the textbook that elevators should be 40% of the horizontal tail and rudders also 40% of the vertical tail. To control it, we use servos mounted in the wing for the wing ailerons. And then for the tail, we used servos mounted in the fuselage. Then on each control surface, we had a 3D printed control horn that was super glued onto it with a push rod attached to the servo and the control horn. Next slide.
For the fuselage design, the main design point was to keep the fuselage as light and compact as possible. With the project requirements not specifying a payload, the fuselage only needed to mount the motor and hold the other avionics. Hence, the maximum diameter of the fuselage was less than 4 inches. The main purpose of the fuselage is to connect to the lifting surfaces. And so as you can see, we had airfoil shaped cutouts for the wing and both tail pieces. And this was done to minimize the drag that we had seen in other mounting mechanisms. And this kind of minimized any additional drag that we would have from other mounting mechanisms. Finally, the fuselage had an elliptical taper, which was used to optimize the structure for the bending moment created by the horizontal tail and the total tail weight. And this taper put more material further away from the neutral axis, giving the fuselage a stronger structure overall. Next slide.
So the next thing we determined was where our propeller would be on the fuselage or wing. The two options we had were for a fuselage mounted or a wing mounted propeller. We chose fuselage mounted because it had a higher weight to thrust ratio and it wasn't limited. The propellers weren't limited in size by the fuselage being right next to it if it was on the wings. And secondly, we chose a tractor propeller, which is located on the front of the fuselage rather than the back, because it would have been an undisturbed flow, which meant we would have had a higher efficiency for our plane or for propeller itself.
So talking about the electronics and motor selection, we were fortunate to receive a motor spreadsheet from Design Build Fly that had over 1,500 motor, battery, and propeller combinations on it. We were able to sort through all of those, and we wanted to provide two different possibilities when we did our analysis, one which would prioritize a more powerful design and one which would prioritize efficiency. We ultimately decided to go with a more powerful system just because we wanted to make sure that we had sufficient thrust. When we went through all of those options, we chose our selection based off of thrust, flight time, and weight. We decided to have a margin of safety of about 25% on the thrust that we calculated for the aircraft. We wanted to make sure that there was no chance that the aircraft would be underpowered and that we'd always be able to get enough lift and velocity. You can see on the slide the battery and propeller that we chose. The propeller, we were capped with a propeller diameter of 9.5 inches. That was due to how we decided to design the ground clearance and the landing gear structure. We didn't want to have too much of a gap, but we also wanted to ensure that there were no ground strikes from the prop. Next slide.
So we went with a tail dragger landing gear arrangement at the recommendation of Dr. Dong. We thought it would be simpler to manufacture and easier to fix upon crashes. For the front landing gear, we went with a double strut just so that it wouldn't want to twist on hard landings. And the height of the front landing gear was determined by giving adequate propeller clearance for takeoffs and landing. We put them into the fuselage with a lightweight PLA spacer. We noticed a lot of other groups had punch throughs of their landing gear through their fuselage, so we wanted to give it a thicker base so that punch throughs would be less likely to happen. And we used 4mm steel bar stock because that was the size of the axles on the wheels we selected. We also used a steel crossbar to ensure that the wheels would be parallel so we wouldn't track left or right on takeoffs. The rear landing gear was a pre-bought, prefabricated arrangement, and we used as light as we could go with our plane weight. And we also printed a rear landing gear spacer. That's an extruded NACA 0012 airfoil. And this spacer was so that we could have a 3-degree angle between the front and rear landing gear so that we could have the 5-degree incidence angle for takeoff we'd calculated before. Next slide.
Our tail design was selected based on similar general aviation aircraft presented in the textbook we used. No significant support was made in the way of external attachments, so all mounting was internal to the fuselage to reduce drag, and they were located approximately 24 inches behind our center of gravity. Sizing was determined using volume coefficients for general aviation aircraft, and then that volume coefficient is also calculated using the wing planform area, wing average root chord, and wing span to determine sizing. And then the aspect ratio was, the wing dimensions were adjusted to make sure that aspect ratios fell within expected parameters for a general aviation aircraft. Taper was also modified to make sure that it would fall within an expected range. Next slide, please. We performed an aerodynamic analysis of our wing using XFLR5 to ensure that the bending moment would not exceed our expected parameters and that the lift characteristics were as expected. Next slide, please. For our structural analysis hand calculations, we did the following method. An elliptical lift distribution was assumed, which allowed us to use the following distribution on the right. And then you can integrate lift as a function of wingspan position to find shear, and then integrate again to find the bending moment. And then knowing that the bending moment will be maximized at the root, the bottom right formula can be used to calculate a maximum expected stress of 3,300 PSI. And then that can be compared to the yield strength of lightweight PLA, which using a safety factor of 1.5 gives us an expected stress of roughly 200 PSI less than our allowed stress limit. Next slide, please. We also performed a structural analysis using software in SOLIDWORKS Finite Element. We applied the elliptical stress distribution across the upper surface of the wing normal to the horizontal plane and found that the maximum stress occurs at the root of the wing as expected at approximately 1,800 PSI, which is a large difference from our analytical answer because of the skin of the wing vastly increasing the area moment of inertia of the wing and then thus reducing the stress that occurs at the root. Next slide.
So we also performed a stability analysis on our plane initial design. The first part of that was a static stability analysis where we determined the moment components from each lifting surface, roll, pitch, and yaw moment. We then combined those and used that to convert to the coefficient of moment and combined each of those with their other respective impacts, such as the high wing, which you mentioned earlier, and the sweep angle. All of our components were, all of our design was stable in each direction. And our lateral and directional stability were stable entirely, and every component that contributed to that coefficient was stable as well.
So tested the dynamic stability of our aircraft using the software XFLR5. Here we have the two flight modes associated with longitudinal dynamic stability. The phugoid mode is characterized by slow, long period oscillations in which the aircraft pitches up and down while maintaining speed and altitude. An optimal eigenvalue for this mode should be negative, but small in magnitude, indicating that the oscillations are damped over time. Based on our eigenvector and eigenvalue, our aircraft is stable when it comes to this mode. And for the case of short period mode, this mode is characterized by the oscillation of pitch angle and acceleration in response to angle of attack. For this mode, an eigenvalue with a large negative real part is desired, which indicates that the oscillations decay over time. From the nature of our eigenvalues and eigenvectors for these modes, we can tell that our aircraft is dynamically stable when it comes to the longitudinal case. Next slide, please. And here are 3 flight modes associated with lateral dynamic stability. Our roll mode is slightly unstable. However, an unstable spiral mode, or excuse me, our roll mode and Dutch roll mode are stable. It's our spiral mode that is unstable. However, a unstable spiral mode is not as important to the overall dynamic stability of the aircraft because of slow response times. And ultimately, this analysis concluded that our aircraft was dynamically stable. Next slide.
So with the calculations out of the way, we were finally able to go ahead and start manufacturing the aircraft. Our first iteration used a combination of lightweight and normal PLA for the fuselage. The normal PLA was used in places of high stress concentrations, like where the wing cutout was. Similarly, all the lifting surfaces were also made out of lightweight PLA, and they were attached to the fuselage via cutouts and epoxy. Let's see. And then the different sections of the wings and the fuselage were also attached with 3D printed tabs and epoxy as well. Finally, the control surfaces were installed with rods that ran through the length of the wing. And ultimately, this was changed in later iterations for the plane. Next slide. So this was our first test flight here. It successfully proved that our aerodynamics were sound, and the plane actually took off sooner than we expected it to, with plenty of power. However, as you can see in that video there, our gyroscope was a little too sensitive and caused the plane to oscillate, leading to a failure in the wing along one of the print lines. Another issue we had with this plane was the center of gravity was also too far forward, which meant we had to add 2 pounds of weights to the nose of the plane. And then you go on the next slide.
So following this first failed test flight, we wanted to address some of the structural issues we saw, and we decided to go with full carbon layups for all the lifting surfaces, both to address those structural failures we found with the lightweight PLA, as well as to get the carbon layup extra credit. Only the steel landing gear pieces and the propeller survived the first crash. We also shifted to a longer nose cone to shift the center of gravity forward. The last plane had a center of gravity at about the half chord line, and we wanted to get it more towards the center pressure of the wing at about the quarter chord line, or even a little further forward. So we used a high density structural foam and a 4-axis CNC foam cutter to cut the lifting surfaces. The only change we made from the first plane was to make the vertical tail have a vertical trailing edge, because the swept design we had originally made couldn't be cut with the foam cutter I was using. Then we did 3D printed PLA wingtips and did a single layer carbon fiber wet layup over the whole thing and let it cure in place instead of doing a vacuum bag. These lifting surfaces were then reinforced with carbon rods, 1/2-inch rod for the main wing and 1/4-inch for the tail pieces. Then our fuselage was reprinted in regular PLA, because those were the only pieces of the fuselage to survive the first crash. And that was wrapped with a single layer of fiberglass to reinforce it and better bond together the sections. Then our motor was updated as our last one. It was no longer usable. Next slide.
So for this test flight, we confirmed that our aerodynamics are good for the second time. And if you play the video, you can see that the plane gets off the ground really easily. We also confirmed that our structural strength was good this time. The plane takes a pretty bad nosedive, but it held up really nicely on the impact. This was thanks to the carbon fiber and the fiberglass layups that we did over the control surfaces and the fuselage. The plane did crash on this flight due to weak attachments between the servos and the control surfaces. This made our pilot lose control of the rudder, the elevator, and we could not pitch up. So that led to that nosedive. Next slide.
So after that flight, only a couple things broke. Our propeller broke with the nosedive, so we had to find a new propeller. And then the fuselage, the nose cone broke completely. So we 3D printed a new one of those. And then the fuselage, about an inch of the fuselage, which attached to the nose cone, cracked. So we super glued the cracks together and then did a fiberglass layup over it to make sure it was structurally sound. And then the landing gear broke a little bit, so we had to re-epoxy that in place. And then the wing had a crack down one of them, so we had to add some epoxy under that. Overall, it held up pretty well with the crash. For revisions, we completely redesigned the control surface or the control horns, as that was our main point of failure. We increased the surface area and then added fastener attachments so we could screw it into the wing, as well as instead of using super glue, we used epoxy to attach them. Next slide, please.
For the third and fourth test flight, you can play the video. This showed our first successful airplane iteration. With the repairs done previously, the plane took off and flew for over half a minute. And this proves our successful airplane design. As you can see in the video, as the plane was coming in for a landing, a gust of wind rolled the plane into the ground during the said landing attempt. And this is one of the weaknesses of the flights, is with no gyro to automatically control the plane, the high winds made it difficult to manually control.
Going into the fourth and final test flight, we were fortunate to have printed an extra nose cone when we went up to the airfield. And so we were able to perform some quick repairs to get another flight up. As you can see in this video, we also had another good takeoff, but it lasted a much shorter flight due to the extreme wind gusts and the changes in thrust that we were requiring in order to maintain control of the aircraft. And we just went into it rolled into a pretty uncontrollable nosedive, and this time the plane was completely destroyed and we could not recover it. Next slide.
So lastly, if you'll go to the next slide, we'll see our takeaways. The design process was very important to make sure that the aerodynamics and the structural strength would be good enough for a flight. This also made the manufacturing process a lot smoother since we knew exactly what we were supposed to do. We learned many different manufacturing methods, whether it was from printing with lightweight PLA, regular PLA, to carbon fiber and fiberglass layups. One thing our group did really well was that every time we came back to fly, we fully fixed our errors from the previous flight. In the future, we think that a larger, lower aspect ratio would be better. Also a better propulsion system, since we had the most trouble with our motors after the nosedive, since they were taking the full force of the impact. And then larger control surfaces, or maybe the use of a gyroscope would help to increase control and maneuverability, but the gyroscope would have to be placed perfectly so that it would not work against the pilot like it did in our first iteration.
Awesome. Thank you guys so much again. We really appreciate your time. And now we're open to if you guys have any questions.
Thank you for the presentation. Great job. I really like it. Let's first ask the feedback and suggestion from the Jacob and Carl first.
You go first, Carl.
Can you hear me?
Yeah.
Okay. Overall, I thought the presentation was really good. Especially the thing that jumped out at me was that the hand calcs were there and hopefully correct. It's kind of hard to know, but the the thing that I really liked was the dynamic stability. That was something we couldn't really like hone in on when we did the presentation last semester. But I was curious whether that spiral mode, I believe, was the one that you said was slightly unstable, if that had anything to do with the like the rolling that you had on your test flight, because it looked like the point of failure, aside from the servos, was always that a gust of wind created instability in your flight. So I was wondering if, and it's not like a yes or no question, but that if that could be possible, a possible source of your rolling.
Yeah, I can take that one. So that's definitely a possibility. We did that dynamic stability analysis was done on our initial design, and as we manufactured, obviously there were things that didn't exactly match up between the two, especially after our first iteration once we went to the carbon fiber. The main one I think about with this spiral mode was our second iteration test flight where we lost our control surface. I don't believe those necessarily were connected. That was simply because we had the rods to connect the control surfaces to the servos. And for the second test flight, we had a control horn, which attached to the control surface itself, pop off of the elevator. So then that essentially meant that we didn't have control of that elevator at all. And once it did start spiraling due to that, because once we went into the turn, we couldn't really control it. By trying to pull out of it, it essentially, since we didn't have half of it, it continued to spiral down as a positive feedback loop type of thing. But for the other ones, we definitely did have a little bit of it. It was a little bit difficult to control, I believe, especially with those wind gusts. So I think it is definitely something we can look into if we were furthering this to see if that would be something to maybe further improve on the plane.
Yeah, what I thought was interesting, at least with our final iteration, was we kind of threw the calcs out the window and used a bigger wing, and therefore we didn't have to fly as quickly. So because we flew slower, but we had more like time to react if there was any gust or anything. So you didn't have to, because like we're not building a race plane here. So it might be possible that a larger wing and then flying slower could fix that. Obviously, it's not that easy to control something that weighs that little. But I thought that was really interesting. Especially, I like the fact that you went with the carbon design, because it kind of saved you in a way with the crashes you had, because nothing really happened that was like unfixable, right? So that was cool. But overall, I thought your presentation was really good, and honestly pretty glad that another group did the carbon design.
Yeah, thank you, Carl. Our first flight, where almost all the PLA just kind of destroyed itself, really kind of pushed us to move in the layup direction. And yeah, if you saw on the second flight, it was a direct nosedive, and really the only casualty was the nose of the plane. So I'm really glad we did the layups as well. Gave us a lot more room for error and to kind of iterate on little things like the control horns.
As of now, I don't know if I have any more questions. I might think of something, but Jacob, you're good to go.
Yeah. Can we go to the slide of your goals?
Pardon, could you say that again? It cut out a little bit on my computer. The slide for the goals?
Yeah, or just like the first slide
Awesome.
where it
Yes.
goes over project scope and stuff.
Let's see. Oh, give me a second. I tried to share the slide on that was already presenting, so I couldn't move. There we go. Can everyone see this okay? Perfect.
Yes. So I might have just missed this, but I think there was like a target slide as well. But did you guys have any specific targets that you were trying to meet, like as a group prior to design, and like how close did you guys get to meeting those targets?
So during our initial estimations, while the maximum flight window of 5 minutes and 3 laps would allow each lap to be completed in about 100 seconds, we were aiming for closer to 60 seconds for each lap. And during our test flight 3, we were getting close to approximately 50 seconds to 60 seconds. So we were close to meeting our internal goal for our estimation for speed during our test flight.
Okay. How much did the plane weigh in the end? Did you weigh it at the end
Do you
of-
want all of the iterations?
just like the last plane?
The final plane was approximately 6 pounds, I believe. So it was about a pound 0.8 for the fuselage, a pound for airfoils, and then about 2 pounds of avionics battery motor mounting and all of the associated servos and push rods, and then another half pound approximately for landing gear.
Okay. And can I see like the picture of like the final plane design? Yeah.
So here is a render we have up here. This is the real physical plane.
Okay. Interesting. Okay. I was just curious. So it looked like you guys' plane was like actually super responsive to roll, and my first two thoughts was maybe because the plane was either like really light, or is also just because like a lack of lateral stability like in real life. I think with the current like fuselage design, you have the wing just going straight through the middle of the plane as opposed to a high wing, and that may help you a lot with actual stability. It feels like you guys tried to design for a high wing, but in this case, it's kind of like the wing is sort of dead in the middle of the fuselage, and I think that's why your plane was so responsive to roll. General comments over the actual presentation. Good presentation, by the way. I would like to see more trades. It seems like a lot of the things here, if you guys sort of mentioned justifying your choices, but if you can quantify those choices and actually compare against like other parameters, it makes it a whole lot easier for me to want to like ask questions, but also just to show like why you made the choices that you did. If you're not doing those trades, it's more like a brochure than the actual like engineering defense. How did you guys size your battery?
So battery sizing was determined based on the motor we had selected, and then running at approximately 75% power for the maximum flight window required.
Okay. Did you have any concerns at all about like the motor or battery overheating?
We did not design for those concerns, and we didn't, of course, run into them during our flights, but I think that is something we definitely would like to address if we were to design again. Our ESC was our electronic speed control was selected as a 60 amp model for our motor, with the motor out front mounted on the nose of the plane. We didn't have concerns about the motor itself overheating, but we did not have any information about possible overheating for the ESC, and we did not design for that.
How
But that
would
would
you
be
design
something
for
we would
that?
like to address.
How would you check for that
If we were to address something like that, I would like to do a prolonged test with the motor spinning at perhaps with the plane mounted in a, I guess just a static location to allow us to give it a spin up and see how the ESC responds to prolonged high speed flight, or I guess high motor speeds, and determine whether the temperature would fall within a safe range. And if it does, then perhaps allowing for cutouts in the nose where the ESC was located to get airflow over it to help cool it.
Is there a way you could do that like analytically in the design phase, like before you even have a motor selected?
I don't know of a way
I can take this.
based on. Sure.
Yeah, you could just use conservation energy and kind of get the heat transfer or heat coming out of the ESC. And then if we had airflow, use the conservation of energy equation to calculate how much heat transfer from the ESC to the air would be.
Okay, yeah, that's what I was looking for. And I'm not going to press you guys too much on it because the flight time is only like 5 minutes. These are off the shelf parts. Just want to see if you had that in mind. Can we talk about your wing loading and calcs? I think it's further down, like the actual hand calcs, MC over I equation. Yeah, right here. Okay. So the yield strength is 35 psi. Is that from the yield strength of the material
Yes,
of the PLA?
yes.
Okay. Is there anything that could make you think that that yield stress would be lower than what the spec sheet gives you?
Absolutely, because it was printed using 3D printing methods, and then the I guess the vertical stacking surface when printing a wing means that the lines of the 3D printing will be normal to where the shear is applied, and it's definitely going to reduce the effective yield strength compared to just a casted piece of PLA.
Yeah, so that's something you should consider when you're doing these initial hand calcs. And I don't know if this is like an adjusted yield strength, but
It is. We used yield strength in the lower 10% of data that we found for possible study on PLA yield strength. And I'm unsure if it was either due to us using a value that was not conservative enough, or if it was due to us using a value provided for regular PLA as opposed to lightweight PLA, and a difference in material properties resulting in a reduced yield strength compared to what we predicted.
Okay, cool. I just wanted to make sure you guys considered the anisotropy, which seems like you did.
Yeah.
It would also be nice to see maybe some shear calculations due to the fact that the stuff is printed the way it is. The bending stress is usually just normal stress, like sigma 1, sigma 2. It doesn't really consider the shear stresses acting on the wing as well. And also combined loading from the drag as well. What loading scenarios did you consider when you did these hand calcs?
This was just steady level flight, lifting only. So this would be the elliptical lifting distribution for the weight required to lift our plane at, what was it, 3 times approximately the weight of the plane as the maximum why not.
Another another quick comment, kind of, we were discussing about the you know, you were saying, is this appropriate? Do we account for that? For the first iteration, obviously, we did not have structural, good structural strength, and that actually didn't fail at the root of the wing, like we kind of assumed here. We didn't account for the stress concentrations that resulted from us, in our PLA to insert our servos into the, to mount them, we had a cutout into our wing, and that is ultimately where the wing failed, because it was not only the issue with the anisotropy of the layers of the PLA, but on top of that, we also ended up having a cutout, which was a corner and a smaller area overall. So that's kind of, I think, where we ultimately did not account for with our structural analysis.
Yeah, so one thing you could have done just to help with the stress relief on the actual PLA itself, you could just like brand tape across the span of the wing, and that would help a lot with the layers being unloaded. I got off track. Yeah, so is this your worst case loading scenario? Steady level flight?
This is the calculation we did, yes, but we did not do any worst case loading scenarios compared to this.
Okay. In general, in structural design, you should always consider your worst case loading scenario, worst case possibility when doing your design. In that case, that would probably be just probably max level flight at like max install angle. or high speed flight at max fall angle, as well as a landing scenario in which it's the way of the wing times the deceleration of the thing rapidly hitting the ground.
That's also the same thing I want to comment on. So you want your structure to be safe in the worst situation, not in the steady level flight. That's what I mean. So that's also reflected in your calculation. It should be in the Nmax, the load factor, maximum load factor. So what load factor did you use when you did the calculation?
It was approximately 3.3 times the weight.
Okay, that's good.
Yeah, so it wasn't a combined scenario with drag and like impact on the ground during landing, but we did use about approximately 3.3 times the weight of the aircraft.
Okay.
The expected weight of the aircraft, which we, at this point in the design phase, would have been approximately 4.5 pounds is what we had estimated at that point.
Yeah. Sorry, interrupt, Jacob. You can continue.
Okay. Let's talk about the next slide. So this is a comment that's like basically made in like every single like Mech 3 or AO presentation, student design presentation. But it's much better to have no FEA at all than bad FEA. SolidWorks FEA is, for one, really bad. And it assumes like isotropic properties of your wing. I am skeptical of these results and if they're accurate at all. So is there anything like that you did here? Like, how did you constrain this? How did you run it?
We constrained it with a lower expected yield stress than the hand calculations were run with, but there was no other specific constraint taken for anisotropic materials.
Okay, yeah, so I doubt how accurate this FEA actually is then. For one, like SolidWorks is limited on their mesh size. It assumes fully isotropic properties. It doesn't account for print layers at all. I would be very skeptical of this FEA. Let's talk about your carbon manufacturing. Can I just get the picture of the wings? So Cam actually told me about this. I think he said composite TA for you guys. I just want to say like how you guys made the wings. Like it was kind of weird when you told me about it, but it's actually super clever. So good on you guys for that. I probably never would have thought of making it this way. So I think that's really cool.
Yeah. Yeah, we wanted to keep it as simple as possible because we were on a pretty expedited timetable after the first crash. And I mean, the first wing took about a week total to print. And I figured if we really simplified the carbon layout process, we could definitely turn it around faster than that with a lot superior structural characteristics.
Where did you guys get the idea from?
I've done a lot of research with Dr. Ify's lab doing carbon foils. So I just kind of used those resources. Like those stands you see me using in the picture, we had used like a week before for another drone. So I just kind of reused some of the stuff we had in the lab to pump out the surfaces pretty quickly.
Yeah, in terms of like actual like quality carbon fiber manufacturing, this isn't like the best way to do it, but for the scope of what you guys are doing, like for the scope of what you guys are doing, this is like very clever and good use of resources. So good job there.
Thank you.
Did you do any pre-flight tests prior to flying?
The extent of our pre-flight tests was holding up the wings in like really gusty conditions and being like, oh yeah, this has a lot of lift. And we also weighed all the lifting surfaces and found that they were much lighter than the printed iterations while being a lot stiffer, but nothing like quantitative, which we probably should have.
Some other tests we did quickly run were we always ended up testing our taxiing, obviously all our control surfaces. So we ran a taxi on a video of us taxiing the night before our first test, which was very exciting. And another test that we ended up doing a little bit, this were like last minute, was before our third test flight here. We did have issues with the motors. We had to switch between the first and the second test flight, but obviously the second one crashed as well. So we ended up to kind of ensure that our motor was safe to fly. It would not cause another crash that would require an entire redo of the plane. For the third one, we ended up holding it statically and running the motor up to probably 75, 100% of the, like, we basically ran it for the range of the power and kind of assessed if we were good to actually run with it versus trying to scrap the flight and go and again another day.
Okay, yeah, that's all great. That you could save yourself a ton of testing time and pain if you do those type of tests. The main test that we did that I was looking for was taxi testing, CG testing, and control surface testing, which you guys all seem to do. Okay. In general, just overall comments. Great job, guys, again. I think it'd be nice to have like quantifiable goals that you can track back at the end of your presentation, see if you meet your goals, do you exceed them, by how much. Just like cost targets, weight targets, which you guys sort of had, just having all in one spot is nice. As far as the choices you made, again, it's nice to have trades of different choices and why you settled down on the final target. As far as instead of just saying like, oh, we picked this because of this. That's something that you generally want to do in like any engineering presentation. For the structures and particularly, again, consider the maximum loading scenario, and that's just landing and also like very adverse flight conditions, not just a steady level flight, because if you notice there's actual flying, like you're only flying steady level flight for maybe like 10% of your actual flight. And then as far as the actual aircraft itself, I would try and root for a actual higher wing. And then carbon fiber was good to reinforce the wing, but if you're doing PLA, at least like taper or something to help relieve those stresses. Yeah, that's pretty much all I got. Good job, guys.
Thank you.
Thank you.
Thank you so much
you.
for your question and suggestion feedback. I think Carl has one more question.
Yeah, can we go to the slide about the wing really quick, like the airfoil selection? Yeah, that one. Okay. So I might have maybe not caught all of it, but what was the particular reason why you chose the 2000 series versus the 4000 series? Like, how did you settle on it? I know that you said you were comparing it, but like quantitatively, I was a little curious because we also, I think, looked at this and we came up with a different conclusion. So I was just wondering if you could run me through that really quick.
Yeah, we looked up a lot of stuff online. We saw that the 2412 is a bit smaller, like less thick than the 4412. So it had a lower drag coefficient. It also, the 4412 also had a higher lift coefficient, but since this was low speed, we found that the 2412 was a little bit better. I mean, they are very similar on the coefficient of pitch versus angle of attack graph. This kind of pushed us to pick the 2412 because we saw that it was like a little bit less destabilizing just because of that it's a little bit less negative. Those are basically the factors that we took into it, and we just made a decision.
Yeah, so the plot shows that your CL over CD is higher for the 4412. And if I remember correctly, the moment coefficient should be more negative for static stability. So was it just a packaging constraint or manufacturing constraint? Because theoretically, if you use the 4412 and use a longer wing, you get a higher Rose number. You'd be in a region of higher stability. So you'd get those oscillations, not that you would really care about it since you're using a positive alpha anyway. But those initial oscillations between 10 and 5, I predict will be gone for the CM. And your higher Reynolds number would make your plot smoother and likely have better seal over CD and CM. Did you look at any other constraints aside from those two, or?
No, we didn't. We probably should have looked into it more. We also, I think we went with somebody correct me if I'm wrong. We also went with the 2412 just because we were more familiar with it and for manufacturing purposes.
So I think I have the same comments here. I just want to ask this one. I think I have the same opinion as Carl. Just want to ask you one in a more straightforward way, because since now you are doing a comparison here. You are showing the lift drag ratio and moment coefficient performance as change of angle tag. So from these two graphs, I think I have the same opinion as Carl. It's basically you are giving this two comparison and showing us actually the 2000 series is actually better. And I mean, you need to give us a better explanation why you are showing these two comparison while you choose the other one.
Yeah, I can try. So for the CL versus CD, I mean CL L over D versus alpha graph, we decided that the increase in L over D was not as important as the correct me if I'm wrong, Maddie, but we think that the coefficient of moment versus alpha, we wanted it closer to 0 for the wing, since the wing is a destabilizing part of static stability. So we were thinking that the large magnitude of the NACA 4412 coefficient graph, that was more negative, I mean, more hurtful than the gain we would increase by the L over D for the 4412. So did I explain that well?
I believe the CM is better to be more negative, right? I mean, correct me if I'm wrong, it's been a while, but.
I thought that was CM alpha. Like if CM alpha is negative, then you have.
Yeah, that's what we're dealing with here, because your CM is CM alpha because you're city level.
Yeah, but wouldn't that be the slope? Like CM alpha would be the slope of these lines, right?
Your coefficient is like you want it to be more negative, I think. I mean, it doesn't like this wasn't like oh you guys did something wrong. Like obviously the plane flew. I was just curious because I also looked at this because I did the wing for our plane. So I don't even remember what other, I know I did like thickness and things like that, but I was just curious. And then the last thing, which is kind of a fun question, if you were to like have a budget and you could only fix one thing, what would be the one thing that you would fix or improve? Like, what do you think was the biggest defining factor? Because I think you had it on the last slide, so it was like in the future or whatever, but and everyone might have varying opinions, but I was curious what you would think would have the biggest impact. Because for me, I think it might be the wing, like either the position or just how big it is. But I was curious what you guys think, given that I wanted to ask a little fun question before
I would say I think that I would just buy a nice flight controller and throw it in the plane. I was the pilot and it was not an easy task, so that's what I would do.
I think it'd be nice if we had a larger surface area wing too, so we could go at lower speeds. It'd probably be easier for Matt to control.
I'm gonna have to agree with.
Yeah, I think I would agree with that too. Obviously, I wasn't the pilot, but we found that flying slower was a lot easier than quicker. So, but cool. Again, really great presentation. I just was curious.
Thank you, Carl.
Thank you.
Thank you so much for your question and the suggestion. So overall, great job. I really like your presentation. It's very clear and the other slides is very comfortable read, and the whole thing is very in a logical way, and also of course the performance of your group for the whole semester. I really appreciate the strong effort, and happy to see the significant improvement after each test flight. You guys actually really solved the problem like in the test flight in the previous test flight. So and some small comments, some comments on like places, small points. So one is the page 15. Yes, so I'm just curious, the figure 17, bending moment of wind for various angle attack. I really cannot see what each line means. I cannot understand this graph.
I'm sorry, I can zoom in some. This slide was very, I ended up doing the slide like arrangement, and I think I spent 20 minutes to get everything on the slide. So I had a feeling that this wasn't the best.
Yeah, probably best way, if you really want to show this one, just use a single slide to show the whole thing. So I can really read what you're seeing on the left and to understand the graph.
That makes sense, thank you. But yeah, here's the, if you would like to look, it's obviously the separate lines are different angles of attack as shown on the left. And this is kind of a, looking at the wing from the front, similar to above. So the x-axis is on the, x-axis of the wing, and the bending is the y-axis.
Okay, so this is generated from what software?
This was generated in XFLR5.
Oh, okay. So it can actually show the bending moment result at a different location, at different angle attack.
Yes.
Wow, that's cool. I never knew that. So, and another thing on page 16. So I think the when you do the presentation, the explanation part was correct, but just the thing you put on the slides may be a little confusing for structure people. You said assume the lift is a shear force. Don't say that on the slides, because shear force is shear force, lift is lift. Shear force is equal to integration of lift distribution. Lift or lift distribution external force, shear force and bending moment are internal force generated by lift. So I think in the presentation part, when I listened to your presentation, it was correct. You guys really said like integrate the lift distribution, you get shear force, integrate shear force. That was correct. But for pure, if I just like read the slides, assume lift is shear force is. I would prefer not to say that.
Awesome. Okay, I'll make sure to change that before I send you the updated slides.
Yeah, and also on page 17. So same comment as Jacob. Try not to use SolidWorks to the FEA analysis, because SolidWorks is really not a professional software for FEA analysis. If some of you took the FEA before, most of our professors use the Abacus, or you can also use ANSYS, but try to use some, like, if you really want to do the FEA analysis, use some professional software. And also one thing I can see that, oh, sorry. So you guys explained, I didn't quite get it. So you guys explained a larger difference from the analytical, So what was the reason you guys feel?
The analytical solution was done using only a wing spar, where the SolidWorks analysis was conducted with a full wing lifting surface, which has both the skin of the wing and the spar contributing to the area moment of inertia.
Yes, I agree with you. So my question is, so in your FEA analysis, why didn't you just use a wing spar to do the analysis?
We also did just a wing spar, which agreed with our analytical solution. And then we presented the solution for the wing that we were modeling to meet our requirements for the project.
Yeah, so what I mean is that since your hand calculation is calculated based on the wing spar is the major load carrying structure, and the calculation is based on only focus on the wing spar. So I would prefer to see when you do it in the software, just model as like the
just using the wing spar. Okay.
Yeah, because in actual situation, the fuse, the skin really does not carry much load, especially in the first iteration you use lightweight PA. The lightweight PA cannot carry the skin is like, I don't know if you use 1 layer or 2 layers, it really cannot carry much load for the bending, especially for the bending. The main load carrying structure in your wing should be the spar. So I think it's very reasonable when you do the analysis, including the software analysis, just consider this line load distribution on the wing spar, and you're done.
Okay.
Yeah. And another thing is, is that in the first, on page 22, oh, I think I got it wrong. So the rods you use is for control surfaces, not wing spar.
Yep, only for the control surface. They formed the axle that the control surface rotated about.
Okay. And one thing I'm just curious since Jacob and Carl here. Because when I communicated with you guys during the test flight, you said you use the fiberglass to wrap around the fuselage, because one reason you did that because to make sure that the signal can transmit through the fiberglass. And I don't know about anything about composite, but I'm just wondering, like, if the carbon fiber, if we use the carbon fiber wrap around the fuselage, will interrupt the signal transmission.
Yeah, I think so, because carbon fiber is conductive. And so I was talking to some of the PhDs in my lab, and they strongly encouraged to not use carbon fiber for the fuselage and instead to use fiberglass, because it is signals transmissive.
Yeah,
we're gonna have all of our avionics inside the fuselage. So from people I know that have done carbon fiber fuselages in the past, they've had to use antennas protruding from the fuselage, so they're not being blocked by the carbon wrap. I heard it described as, doing a carbon wrap of a fuselage is turning the whole plane into a Faraday cage.
That's essentially a Faraday cage, and that's something that we are concerned about when we wrapped our plane in carbon fiber, but it was not an issue. You're flying at such a close range where it's not a huge issue. And Group 1 also wrapped their fuselage in carbon fiber, and it's fine. In a general sense, that should be a design consideration if you're flying long range and really far away, but for such a short plane, you can wrap it no problem. Fiberglass is heavier, but it's also cheaper, and for the stiffness requirement that you need, it probably works just as fine.
Okay, great, thank you. And I think that's all the question I have. So thank you for the great presentation, and thank you for the hard work throughout the whole semester. So one thing I want to ask, did you guys finish the class evaluation? Because I checked the response rate this morning is still very, very low. And I think it's due tonight. So I would really appreciate you can take several minutes to submit the class evaluation, because this class, I still consider it's in the stage of test round, because, this is the second semester we tried this in the aircraft design this way. So I definitely need a lot of feedback and suggestion on how to improve the teaching for this class, so I can make this class better. And you guys are the only person who can give me the suggestion and feedback, so I'm kind of dependent on you guys. So I would really appreciate that you can submit the class evaluation.
Of course, I'll make sure we all get it done after.
Thank you so much. So thank you for the presentation, and have a great day.
Thank you so much. Have a wonderful day.
Thank you. Have a good day.
Thank you.